This is the second lecture from Chapter 5, Polarity of Molecules, and we've just finished talking about how to determine the shape of a molecule, and you need to know the shape in order to make a determination if the molecule is polar overall. So the first thing I want to make sure is that you understand what polarity is. When a chemist says something is polar, they are indicating there's some degree of separation of charge. So it doesn't have to be a full ion, like a cation and anion. There can be partial charges. And that happens when you have a molecule. There may be no separate ions, but there may be a higher electron density in one portion of the molecule than the other. And if that's the case, that molecule is polar. And that's important. That affects reactivity, and mainly reactivity, but a number of important facets for the molecule. All right, so polarity, just to kind of give you a visual and tell you how it's confirmed, how it's measured. So let's, for example, look at hydrogen monofluoride, okay, HF. So we know that fluorine is the most electronegative element on the entire periodic table. And hydrogen, hopefully you realize that it's pretty electropositive. It's not electronegative at all, okay? And so, not surprisingly, when hydrogen bonds with fluorine, because fluorine is so electronegative, it's going to hog those shared electrons. And so you're going to have what we call a partial negative portion of the molecule and a partial positive portion of the molecule. And that's going to be a real polar molecule overall. That can be confirmed if you put the samples in the presence of an electric field. You will see the little molecules lining up just like you would expect. Okay, the negative end of the molecules, that would be the fluorines, all pointing towards the positively charged plate, and the electropositive end pointing towards the negatively charged plate. All right, so we have talked about polar bonds a little bit, and that the polarity of a bond is determined by the difference in electronegativity between the two elements that are forming the bond. And we gave a range. We said, okay, if the difference in electronegativity is less than or equal to 0.4, we call that a nonpolar bond. So in that case, the two elements are sharing very close to equally, if not totally equally. And that if the difference in electronegativity was in the range of greater than 0.4 or less than 2, we called that polar covalent. So it's still a covalent bond, but the bonding electrons are shared unequally. They're closer to the more electronegative element. And then if the difference in electronegativity is greater than 2, it's an ionic bond. All right, so just kind of a refresher, how to identify polarity of bonds. Now, just because a molecule has a polar bond does not necessarily mean that the molecule is going to be polar. Okay, so that sounds weird at this point, but I'm going to explain it. So a couple more just kind of vocabulary when we talk about polarity is chemists indicate polarity either with partial charges. So I showed you that before, but you'd put like a partial negative over or next to the element that's more electronegative and a partial positive over the element that is less electronegative. Or you can draw what we call a dipole, okay? So it's an arrow. Okay, the tip of the arrow points to the more, or is over the more electronegative element. So look at it on hydrogen fluoride. This tip of the arrow is over the fluorine, the more electronegative element, and the other end of the arrow has a cross. I always think of that as a plus sign because the plus sign, is over the electropositive, the less electronegative element. All right, so you can, once you draw the shape of a molecule, you can draw dipoles for every polar bond. So see, the arrow is over the more electronegative element, which is chlorine in this case. Now, I hope you notice that there is no dipole drawn for the carbon-hydrogen bond. And that's because the carbon-hydrogen bond is nonpolar. They have such close electronegativity values that it falls within that less than or equal to 0.4 range. If I'm remembering correctly, I think the electronegativity of carbon is 2.5 and that for hydrogen is 2.1. And so the difference in electronegativity between those two elements is right at 0.4. So carbon-hydrogen bond is always a nonpolar bond. I would write that down, highlight it, and tuck it in the back of your memory. That'll come in handy several times throughout chemistry, okay? It's just kind of a good thing to know. All right, so so if you draw a dipole, and I want you to be aware that you may see a problem that gives you the dipole moment for a molecule. That means that if there is a dipole moment, that means that that molecule is in fact polar, okay? So all of these molecules have a permanent dipole moment. They're all polar. And polarity or dipole moments are given in units of debye, capital D. So I just want you to be familiar with that if you see that, okay? All right, so we're going to start applying this. We're going to start drawing shapes of molecules and determining whether or not they're polar. So I want to give a summary of what the rules are for a molecule to be polar, all right? So for a molecule to be polar, number one, it must have at least one polar bond, okay? A polar bond being defined as the elements making the bond having a difference in electronegativity of greater than 0.4. There is one exception, and this is a specific example of that exception that you're likely to see. Ozone, O3, all right? There are clearly no polar bonds, okay? Oxygen with oxygen, two oxygen atoms have the same electronegativity, so those bonds themselves are not polar, but the molecule overall is polar. There is a permanent dipole. How is that possible? Okay, so and that's because on the central atom you have a lone pair of electrons, okay? Lone pair of electrons are much more electron rich because they don't have to share with another element than bonding electrons are. So overall, the top of this oxygen has a richer, more dense electron density than the rest of the molecule, and that gives it an overall polarity. So anyway, but for 99% of them, you're going to have to identify that there is at least one polar bond in the molecule. Now, having a polar bond is not enough. The molecule must also be unsymmetrical, or that can also be called asymmetrical. In other words, let me put this a positive way. If a molecule is symmetric, that means it cannot be polar, okay? If a molecule is symmetric, it cannot be polar. So it doesn't matter how many polar bonds you have. If the molecule overall is symmetric, it cannot be polar. So what do I mean by symmetric, okay? That's going to be probably the trickiest part for you, okay? Symmetric means that regardless of what plane you fold the substance in half over, so let's call that the y plane, and then fold this over, and it's identical, right? If you fold it over, the two sides meet each other exactly. So this is symmetric along the y-axis, but that's not enough, okay? It has to be symmetric along all axes. So if we folded it the other way, it's also going to fold over exactly. The approach that I have always taken, because I don't visualize very well 3D in space. So what I have used, and I share that with you just in case it might help you, is I imagine that I am a person, or that some person is the central atom, and that there are people around them. In this case, this model, there are three people standing equally spaced around them, and that all three of those people have equal strength, and they are all pulling with equal strength on me in the middle. Now, if all these people are equal strength and they're pulling with equal strength, am I going to move being in the middle? No. Okay? That's a sign of total symmetry. Now, just to give you an example of what asymmetry would be, what if one of these people on the outside of me was larger than the other and could pull with much stronger force, okay, than these little guys, okay? That would be, this molecule would then be polar, okay? So if any of one of the outside atoms is different than the others, okay, then it's gonna end up with a net dipole. It's going to be polar, okay? So in general, and you don't necessarily have to remember this, the examples, you'll learn it on your own. But these are shapes that if all of the exterior atoms are the same, those are shapes that are always symmetric. And again, the exterior atoms have to be the same though. Now, on the right-hand side, the right-hand column, these shapes, even if the exterior atoms are the same, these shapes will never be symmetric, okay? And let me show you why. So imagine this is a water molecule. You can do it the folding along the axes, right? So if we fold along that axis, it's symmetric. However, now let's fold along the x-axis on that water molecule. Okay, so fold that way. If we fold up, they're not the same. There's nothing up here, okay? So that is not a symmetric molecule. No matter what, you can't make it to be. And so these shapes will always be polar, okay? So bent will always be polar. Trigonal, pyramidal will always be polar, okay? And any diatomic molecule will clearly always be polar. Alrighty, so if you're the type that likes flowcharts, the logic of flowcharts, you could use that too. So just to kind of reiterate, in order for a molecule to be polar overall, there has to be at least one polar bond. We have that little exception, but in general, there has to be at least one polar bond, and the molecule has to be asymmetric, okay? Moving on. All right, let's look at some examples. CO2, carbon dioxide, okay? If you didn't know the shape, I don't know, what if you just didn't know the little structure, didn't know the shape, and let's say you drew it like, kind of like a water molecule bent, okay? You would say, oh yeah, that's polar. The carbon-oxygen bond's polar. I know the carbon-oxygen bond is polar because oxygen's a lot more polar or electronegative than carbon, but you'd be wrong. So again, it goes all the way back to our Lewis structures. That's the basis for everything here. Draw a good Lewis structure, be able to determine the shape. Carbon dioxide is linear. So overall, it is nonpolar. So let me show you how you would demonstrate that, how you would show your work to demonstrate that it's nonpolar. Because on a test, you're probably going to be asked, why is this not polar, okay? And you might say, well, it's linear. Well, that's kind of an explanation, but it's not a thorough one. What you would have to say to explain that is that carbon dioxide, although it has polar bonds, it is linear and the dipoles cancel each other out, okay? That's exactly the language you used. The dipoles cancel each other out, and that's because they go with equal force in opposite directions, okay? So this oxygen is pulling as heavily as the oxygen that is completely opposed to it. So again, think of that person. Think of you being the carbon atom in the middle. You have two identical twins on either side of you pulling with equal force. This carbon isn't going to move, okay? So that means that carbon dioxide is nonpolar. Alrighty. I had mentioned earlier about the polarity of a molecule affecting greatly its reactivity. And the reason it does that is because, remember now, if you have a polar molecule, I said there were two ways of indicating that. One way is to show partial charges, so you should learn how to draw the partial sign. So I learned it by starting to draw a figure 8 and then not finishing the figure 8. Okay, starting to draw a figure 8 and then not closing it. To me, that's how I taught myself. Okay, so that's a partial charge. Or you could draw dipoles, the line. Just remember the arrow goes next to the more electronegative atom, and there's that little kind of plus sign on the other end. All right, so if you have polar molecules, they line up with each other just like they would in an electric field. We know opposite charges attract each other, right? And so the partial negative end of one molecule will line up with the partial positive end of another molecule. And you have a very organized and strong attraction between molecules, okay? What does that affect? Okay, well, first of all, that attraction between molecules is called intermolecular forces, abbreviated as IMF, intermolecular forces. That becomes huge in chemistry, really, really important. All right, because that affects how the molecules associate with each other, how tightly they pack, that affects melting and boiling points, surface tension. I'm sure you have seen that water, all sorts of things can float on water, like paper clips and stuff. That's because water is so polar that it's highly organized, highly associated with itself. It doesn't like to let anything else in. And solubility, okay? So as far as solubility, there's this little ditty that says like dissolves like, and that simply means that polar substances or polar solutes will dissolve in polar solvents. Polar likes polar and nonpolar likes nonpolar. Following through on that like dissolves like, you probably know that table salt dissolves readily in water. And as a matter of fact, the vast majority of ionic compounds dissolve readily in water. And that's because a polar compound, let's just look at table salt, sodium chloride. Ionic compounds are extremely polar. They're the most polar, right? Total, complete separation of charge. All right, and water has a permanent dipole. So if you were to draw the dipole arrows, right? Partial charges are already there, or you could draw the dipole arrows. Water's polar, and so water dissolves polar solutes, okay? And ionic compounds are very polar. That is also why oil and water do not mix. Oil is made of what we call hydrocarbons, and there's a bunch of carbon and hydrogen bonds in a hydrocarbon like oil or gasoline, okay? And I wonder if you wrote down when I told you to a few slides ago, carbon-hydrogen bonds are nonpolar. And of course, as we said, water molecules are very polar. And so the two don't mix. They're not attracted to each other. The general procedure you'll follow for predicting the polarity of any molecules is you will always start out by drawing the Lewis structure and then determining the molecular geometry, okay? Obviously, you can't get a good molecular geometry unless you're able to draw a good Lewis structure. Then determine if any of the bonds in the molecule are polar. So you'll need a electronegativity table. So if the difference in electronegativity between any two atoms that are bonded is greater than 0.4, it is a polar molecule. If you have at least one polar bond, then you have to determine if the overall molecule is symmetric. If it is symmetric, overall, it's nonpolar. If there's any asymmetry, then you got a polar molecule, okay? So let me walk through one with you. Sulfur tetrafluoride, all right? So going through, I'm going to kind of be tedious here, but going through the Lewis structure, right? So count valence electrons, 6 from sulfur, 7 from each of the 4 fluorines. So you have 34 valence electrons to find a home for. Draw, of course, single bonds with all of the fluorines and give each fluorine an octet. When you do that, you will have used 32 electrons, which means you have 2 left over to put in the middle. So I happen to know the sulfur-fluorine bond is polar. Most bonds actually are polar. There's only a handful that have electronegativities close enough to be nonpolar. So we have at least a polar bond. We've met that prerequisite. The other prerequisite is to determine the shape and determine if that shape has symmetry. So walking through that, how many domains do we have around this central atom? 1, 2, 3, 4, 5. So the electron domain geometry is trigonal, bipyramidal. Okay, so get into the habit of being able to draw those, okay? So a trigonal bipyramidal, you have one domain going straight up, one domain going straight down. Remember, all lone pairs go in the equator for trigonal bipyramidal. They have more room. So I'm going to go ahead and put my 3 equatorial groups, and one of them is going to be a lone pair, and the others are going to be fluorine. Now, since the sulfur-fluorine bonds are polar, I'm going to go ahead and draw dipoles. Okay, remember the arrow points toward the more electronegative atom. So I'm hoping that just from this diagram now you can see that these 2 dipoles I just drew completely cancel each other out, right? So if that's all you had there, it'd be nonpolar, right? But you have more, okay? You have these, okay? And you have the lone pair, which has a higher electron density than anything. So this is not symmetric, okay? Whether you try to fold it over on an axis or whatever, this lone pair makes it non-symmetric. Now, if everything was a fluorine atom, they would all cancel out and it would be nonpolar. I'm going to go out on a limb here and say the vast majority of the time when you have a lone pair on the central atom, you have a polar molecule, okay? All right, so we have decided that it meets the prerequisite to be polar all over. A little bit more about the shape, because on a free response question exam, you'd be asked Lewis dot structure, electron domain shape, molecular shape, angles. So we already said that the electron domain shape is trigonal bipyramidal. What is the molecular shape? Okay, that is called seesaw when you have one lone pair in a trigonal bipyramidal. The angles, see the angle between the axial and equatorial is 90 degrees in a bipyramidal, and the angle between 2 equatorial is 120 on the bipyramidal. Okay, so I'm just kind of giving you a review of everything. Alrighty, so here are more practice for you. And I am not going to work them here because I'm going to put this on my as a go-formative participation question. So, but you can go back over the example I just gave you to kind of guide you in doing these. But these are not too hard, the ones that you should be able to do. And that's it for molecular polarity.